Welcome back. And in the last class, in the last video, we have discussed about the first generation solar cells, that is a monocrystalline solar cells and the polycrystalline solar cells. And we have already seen that the monocrystalline solar cells are manufactured by means of a process called Zekulski process, and the polycrystalline solar cells are manufactured by means of a process called casting process. The second generation the first generation solar cells are based on a silicon technology called crystalline silicon technology. The second generation solar cells are based on a technology called thin film solar cells. Right, and why they are called thin film solar cells? In the sense, the thickness of these solar cells are really of the range of few micrometers thickness. You can see few micrometer thickness, micrometer. This is 10 to the power of milli or micro 10 to the power of minus 6 meters thickness. It is a very high length fraction. It's like an X-rays or a OHP sheets like structures. These are very less expensive. Why they are less expensive means because the material which is required to fabricate this amorphous or the second generation solar cells are less, as well as low cost manufacturing. These two things made the solar panels available for a lower price compared to the first generation solar cells. There are basically three different types of second generation solar cells. There are first one is a amorphous silicon, which is a silicon based solar cell, and second and the remaining two are the non-silicon based solar cell. That is, here the first amorphous silicon, the semiconductor which is used for the manufacturing of these solar panels are silicon. By using silicon itself, we'll fabricate the amorphous silicon solar cells. But the remaining two solar cells are the cadmium telluride solar cells and copper indium gallium diselenide solar cells. And these two types of solar cells, the materials which they will be using to fabricate the solar panels are not silicon. They will use these materials. For cadmium telluride solar cells, they will use cadmium telluride material, and this cadmium telluride acts as a semiconductor material. And for the CIGS solar cell, they will use the copper indium gallium diselenide, in short CIGS material for fabrication of these solar cells. Right. Now let's discuss one by one. The first technology is thin film solar cells. As you already seen, you can see on the left side, on the right side, a bottom figure, you can see that is what is called a thin film solar cell. They are very very thin, like X-rays. And then you will see the complete thing. Now the first type of it is a amorphous silicon solar cells. It is these amorphous solar cells are made of silicon only. What is the process by means of which they will be made? It is the amorphous silicon solar cells are fabricated by a process called plasma enhanced chemical vapor decomposition. Right, and the other type, they are of low cost as well as low efficient. The cost is less and thereby the efficiency is also less. They can be rollable. You can see at the bottom there are different solar cells. All are made in USA or some are made in Chennai also. You can see this is how the amorphous solar cells will be like. They will be used like a mat. You can make a solar bag by means of this amorphous solar silicon cell. You can make a solar hat or a cap by means of this solar silicon cell. What is the purpose? You can make a solar cap and you make a solar panel fix on it, and that panel is made of this amorphous silicon, and that by using that panel you will generate the energy. That energy will be used to charge your mobile phone while you are in a traveling. That is how it will be useful. And you can see the right side diagram. If it will be used to charge a camera, this will be very very useful for wildlife photographers, where they will be going in the wild, where instead of carrying the batteries, they can carry these flexible solar panels and they can charge their cameras. The band gap of these solar panels is 1.7 electron volts, whereas the band gap of a monocrystalline and a polycrystalline solar cells are 1.11 electron volts, whereas the band gap of the amorphous solar silicon cells is 1.7 electron volts, used to produce large area photovoltaic solar cell. That is, they require very huge area because the efficiency is less, around 6 to 12% only, and thereby the amount of area required for the same amount of power output is very very high. Number of panels are more. Right. And then coming to the shape, there is no definite arrangement of atoms. In the monocrystalline or the polycrystalline we have seen, even though in the monocrystalline we have same grain size and the same orientation. In the polycrystalline, different grain size and different orientations, right? But here in case of amorphous, different grain size, different orientations, and one more thing, there is no definite arrangement. In the previous case, all are arranged in a definite arrangement in a straight lines, but here there is no such straight line arrangement. So what are the drawbacks, what are the advantages? Means partially shade tolerant, which means even though sunlight, whenever you keep the solar panel under a tree, some amount of that shadow falls on the solar panel, then even the shadow falls on it, it will work, it will partially work. But monocrystalline solar polycrystalline will not work when shadows fall on the panels. More effective in hotter climates, so it will be more useful in the hotter climates. As I already told you, monocrystalline solar cells are not useful for hotter climates, because if the temperature increases more than 25 degrees centigrade, then the efficiency drastically decreases. But when compared to polycrystalline solar cells, they are better compared to monocrystalline. But when compared to but now if you compare amorphous solar panels with the monocrystalline polycrystalline, amorphous solar panels can be used in very very hotter climates. Maybe in the deserts we can use this type of solar panels. Use less amount of silicon and aluminium, so that there is no aluminium frame, as well as uses less amount of silicon for fabrication of the solar panel. So thereby the embodied energy is less, that is the amount of energy required to produce the solar cell is less. What are the drawbacks? It is less efficient. The efficiency will be in between 6 to 12%. They are less popular because they are very harder to replace, and it takes up more space for same output. As I already told you, say the efficiency of this solar panel is 6%, whereas the efficiency of a monocrystalline solar panel is 24%, which means one panel of monocrystalline solar cell can produce, say if it can produce same amount of electricity, which will be equivalent to 4 panels of amorphous solar panels. If the efficiency is 6%, so we require 4 more panels, that is we require 4 panels. 4 panels of amorphous silicon will produce the same amount of energy as one panel of monocrystalline silicon solar cells will produce for the same power output, right? So it's a new technology, thereby it's a less proven reliability. These are all the drawbacks of the amorphous silicon solar panels. The next thing is a cadmium telluride technology. Now the cadmium telluride solar cells. Now this cadmium telluride solar cells, you can see these are called the multijunction solar cells. And actually what I told you is this cadmium, here we are using cadmium telluride as a semiconductor material and cadmium sulfate as one more semiconductor material. Here the cadmium telluride acts as a p-type semiconductor material and cadmium sulfate acts as a n-type semiconductor material. We require 2 different types of semiconductors, p-type and n-type, to form a p-n junction diode. Otherwise it won't work out. So definitely they will be having 2 different types of semiconductors, that is we need one n-type and one p-type. Here the cadmium telluride acts as a p-type semiconductor and cadmium sulfate acts as a n-type semiconductor, and that's why you can see the length of the CDS is very less, 1 micrometer, and length of the cadmium telluride is very high, that is around 100 micrometers. The band gap of cadmium telluride, that is the bottom layer or the p-type layer, is 1.45 electron volts, whereas the top layer CDS, the band gap is 1.58 electron volts. But whereas in case of a monocrystalline or polycrystalline, we'll use a top layer and a bottom layer both as silicons with same band gap, 1.1 electron volt. Both n-type is having 1.1 electron volt and p-type is also having 1.1 electron volt. But here 2 different band gap materials will be used. The top layer is a CDS, cadmium sulfate layer, which acts as a n-type layer, and the band gap is 1.58 electron volts. And the bottom layer is a cadmium telluride, which acts as a p-type layer, which has a band gap of 1.45 electron volt. That is, the top layer is having more band gap compared to the bottom layer, and this n-type and p-type will be combined together to form a p-n junction, similar to that of a monocrystalline solar cells. And after that, the bottom one, the back side, we have a back contact, and the bottom layer on the piece and below the p-type layer we have a below the p-type layer we have a back contact, and above the p-type layer we have three layers, as we have seen in the structure of a the structure is similar. What are the three layers? We have the first one is anti-reflective coating, then metal contacts, and finally glass. The same thing will be there. The only difference is the material with which it will be made. In the monocrystalline polycrystalline of the first generation solar cells, we have used only silicon, but here we are using different semiconductor material other than silicon. Right. So I already told you the top layer, that CDS, is acting like a n-type layer, and CDTE, cadmium telluride, acts as a bottom layer or a p-type layer. There are different here there is this top layer is called a window layer, and the bottom layer is called an absorber layer. They have kept a different names. Window layer is the top layer, that is CDS, and the bottom layer is called the absorber layer, which is called CDTE. And first of all, let's see what is a window layer and what is a absorber layer. Window layer is nothing but a top layer, and it is made of large band gap material that absorbs the higher energy photons. Large band gap material which absorbs higher energy photons. And bottom layer is called the absorber layer, and it is made of smaller band gap material that absorbs lower energy photons which are not absorbed by the window layer, that is the top layer. What is the meaning of this? Let's talk about an equation. E is equal to hc by lambda. We already know about it. H is a Planck's constant, c is a velocity of light. Both are constant, and therefore E is inversely proportional to lambda, that is energy, the band gap is inversely proportional to wavelength. So high energy, here we are using two different types of materials. The top layer is a window layer. I am using a high bandwidth material called CDS, having a bandwidth of 1.58 electron volts, whereas the bottom layer is a CDTE layer called an absorber layer. I am using and this one is having a band gap of 1.45 electron volts. So top layer is having more band gap and bottom layer is having less band gap. Why I have to take like this? Now let's see this explanation. Higher the band gap means high E means inversely proportional to E is inversely proportional to lambda. That is, whenever E is high, lambda is less. Whenever E is less, lambda is more. Right? That's a common observation. That is, high energy means, high band gap means low wavelength. Low wavelength means less distance penetration. Whenever the sunlight whenever the high energy sunlight falls on a material, it will passes through a smaller distance only, up to 5 kilometers, up to so smaller distance. But if low energy, if for example, if the sunlight having less amount of energy falls on the semiconductor material, so less energy means high lambda. High lambda means more distance, but they can travel more distance compared to the high energy. High energy will travel through small distance. And say for example, this is a thing. Let's take it as a solar panel. Whenever sunlight falls on it, if it is a high band gap material, the energy will go through only up to half of this. If it is a low band gap energy, the solar energy can travel to up to the back portion of it. It is how it will be made. Right. Now, what is the advantage of it? So high energy, that is 1.58 electron volts, this is a top band gap. So whenever that amount of energy falls on it, it will liberate the electron hole pairs and electricity will be generated, and the remaining which is not absorbed by the solar cell will be transmitted to the bottom layer, where again the bottom layer will absorb the photons which are not absorbed by the primary layer, because in the top layer the band gap is 1.58 electron volts. So the photons having more than 1.58 electron volts only can be absorbed by the top layer, and remaining will pass through the bottom layer, and this bottom layer will absorb that thing which is not absorbed by the top layer or the window. That is why it is called an absorber layer. Right. Again, you will get that 1.45 electron volts photon will be absorbed by this CDM cadmium telluride layer, and again it will produce electron hole pairs, and thereby second time the electricity will be produced. So that is more amount of electricity will be produced. And as we can know that the back contact is a metal contact which is made of either molybdenum or tungsten, which is also called wolframite, W. And the anti-reflective coating. This anti-reflective coating will be made of either tin oxide SNO or indium tin oxide ITO. ITO means indium tin oxide. These two are acts as an anti-reflective coating, and metal contacts are made of either aluminium or nickel. And the top glass, it is a glass, is made up of a soda lime glass. It is all about the cadmium telluride technology. Now let's talk about the copper indium diselenide, copper gallium indium diselenide, CIGS. Copper indium gallium diselenide or copper gallium indium diselenide. We can call it anyway. Copper gallium indium diselenide, CIGS. Copper gallium indium diselenide solar cells. Here the concept is same. But what is the difference here? In place of cadmium telluride, I am using a cadmium CIGS as a p-type layer, and n-type layer is CDS. It's common. So here CIGS material having a band gap of 1.38 electron volts, whereas the CDS material is having a band gap of, as I told you in the previous slides, 1.58 electron volts. The concept is same. The top layer is called the window layer and bottom layer is called the absorber layer. The top layer will absorb the solar high energy photons, and whatever is not absorbed by the top layer will be absorbed by the bottom layer, and thereby the amount of electricity production will be very high. At the same time, we have a molybdenum back contact here at the bottom, and at the top we have three layers. One is a anti-reflective coating. In this case, then there are two layers of anti-reflective coating are used. One is a zinc oxide. We can use either zinc oxide or indium tin oxide. We can use either zinc oxide or indium tin oxide as anti-reflective coating, and the metal contacts are made of either aluminium or nickel, and the soda lime glass usually which will be placed at the top, now it is placed at the bottom. That is called a soda lime glass is used here. These are called the heterojunction solar cells. So you can see on the right side the diagram of a CIGS. They are very very thin films. It is about the second generation solar cell. Now let's come to the conclusion slide. The highest reported efficiency of an amorphous solar cells is 11.4% so far. What are the advantages? Less silicon needed for production. This amorphous silicon is a silicon based. The material used for the production of this solar cell is silicon. Less amount of silicon is required when compared to monocrystalline, polycrystalline, and thereby it is very very cheaper. It's a thin film solar cell. All these three are the thin film solar cells. What are the drawbacks of this? Photo degradation over time, not much efficient, because there is a process called photo degradation happening onto the material. Thereby it is very very less efficient. Extra glass layer to provide mechanical support, because they are very thin. We need to provide extra glass layer on top and bottom so that it will be costly. So more space required for same power as low efficient. So more amount of space is required for the same power output, because it is low efficient. As I told you, 4 panels of amorphous silicon will produce same amount of energy as 1 panel of monocrystalline solar cell will produce. The second one is copper indium gallium diselenide. So the highest reported efficiency of this technology is 20.3%. The advantages are stable, more efficient than amorphous silicon. So better resistant to heat than silicon. When compared to silicon, it is better heat resistance. It has a better heat resistance capability. So with it increase in heat, the degradation of the material will be less in case of a CIGS compared to silicon. So the drawbacks are not much efficient and more space for the same power. Same concept, not much efficient and more amount of space is required for the same power. So cadmium telluride, the highest reported efficiency so far till date is 16.7%. It is stable. Advantages are stable, highly more efficient, slightly more efficient compared to amorphous solar silicon. Cadmium is very abundant element, so we can make the cadmium telluride solar cells with less cost. Good match with sunlight. What are the other things? The cadmium is a dangerous element. That's why it is a toxic element. Not much efficient. As a result, more space is required for same power. It is all about the second generation solar cells. Now let's see the comparison between monosilicon, polysilicon, and thin film solar panels. What is the difference between these three? It is monosilicon, polysilicon, and amorphous solar panel. That is, monocrystalline is high efficient 21%. Polycrystalline the efficiency is 16% moderate, whereas the thin film the efficiency is the amorphous silicon that the efficiency is 12% only. The monocrystalline solar panels have to be manufactured from a single silicon crystal, whereas the polycrystalline solar cells are manufactured by fusing different crystals of silicon. But here when in the amorphous silicon solar panels, they are manufactured by depositing one or more layers of solar PV material on substrate, because they are very X-ray like when micrometer thickness. One or two layers have to be made on the substrate to fabricate these solar panels. The performance is best at standard temperature. As I told you, the monocrystalline solar panels will perform better at standard temperatures at 25 degrees centigrade only. If temperature increases more than 25 degrees centigrade, the efficiency will go down drastically. Whereas in case of a polycrystalline solar cells, less degradation when compared to monocrystalline. So we can, even though temperature is more than 25 degrees centigrade, it can withstand. But thin film solar cells, that the amorphous solar silicon panels can withstand in a very high temperatures. That is, they can be used at even at 40 degrees centigrade also. There is no degrading in the efficiency. Requires least area for the given power. Monocrystalline solar panels require least area for the given power. Requires polycrystalline less area, and amorphous silicon panels require large area. As I already told you, one panel of monocrystalline solar cell will produce an energy which is equivalent to 1.5 panels of polycrystalline solar panels and 4 panels of amorphous silicon thin film solar panels. Right. So the large amount of silicon is required for the production of both monocrystalline and polycrystalline, and thereby the embodied energy is very high. But in case of a thin film or the amorphous solar silicon cells, the amount of silicon required is very less, and thereby the embodied energy for the production of these panels is less. So, and one more important parameter here is performance degrades in low sunlight conditions. If the sunlight is not proper, then the performance is less. As the solar radiation decreases, less than the standard is 1000 watt per meter square. If it comes down to 800 or 750 or 200 or 300, the performance decreases. But whereas in case of a thin film solar cell, the performance is less affected. Of course it will be affected, but that effect is less compared to mono and polycrystalline solar cells. Coming to the cost per watt of this solar panel is $1.589 US. That is, if I require a 20 watt panel, then the cost will be 20 into 1.589 US. As for the polycrystalline solar cells, it is cost per watt is per watt cost is 1.418 US, whereas for the thin film it is 0.67 USD. The largest manufacturer of this monocrystalline solar panels are SunPower USA, whereas the largest manufacturer of polycrystalline solar cell is Suntech China. Whereas and one more thing, there is a company called First Solar in US based company, which is a largest manufacturer of thin film solar cells. And let's come to the last concept of this unit, that is the multi-junction solar cells. What are these multi-junction solar cells? I already told you the concept is same. In the previous case, we have used two different semiconductor materials. The top layer is a CDS and bottom layer is either CDTE or CDAGS. The top layer is having high bandwidth and the bottom layer is having the low bandwidth. Right? The same thing we are doing it here. What is that? Here instead of two materials, we are go for 3 or 4 materials, triple junction or quadruple junction or pentajunction. We can go for heterojunction solar cells. So far they are made only 3 junction solar cells. So what are the multi-junction solar cells? A stack of semiconductors with descending order of band gap energies. That is, the top layer will be having a high band gap, the second layer will be having a low band, middle layer will be having the less band gap compared to top layer, and the bottom layer will be having the least band gap compared to the above 2 layers. So what happens, say now let's see on the left side we have the top diagram, that is the intensity diagram. So this is solar radiation spectrum. The solar radiation spectrum, you can see what is this band gap. Then we can see the wavelength is on the x-axis. The wavelength is increasing. That is, the purple light is having a wavelength of around 200 nanometers, whereas the blue light is having a wavelength of around 300, whereas the green light 400, red light 800, 600, something like that. So So as the wavelength is more, the amount of energy is less. The band gap is less. So the purple light is having the highest energy, highest band gap. And highest band gap energy means low wavelength. That is, it will penetrate to smaller distance. You can see in the bottom diagram now. The purple light is having the highest band gap energy, can penetrate to smaller distances only, up to the first layer only. Now otherwise, the second, you can see the blue or yellow light, they can penetrate, they have the higher wavelength compared to the purple. That's why the band gap is higher wavelength means lower energy. That's a low band gap. Low band gap means high wavelength. High wavelength means they can penetrate until the second layer. Now you can see the red one, which is having a band gap of around 800 to 1000 nanometers. They have a highest band gap means less energy. So highest band gap means more penetration. They are penetrating to up to the third layer. It is what I explained you in the CDTE and CIGS solar panels also. More wavelength means more penetration. Less wavelength means less penetration. That's it. Less penetration means high wavelength. High band gap. More penetration means low band gap. That is it. Right. So the lowest wavelength, that is the highest energy purple light. Lowest is equal to Hc by lambda. Energy is mostly proportional to lambda. So it is the lowest wavelength purple will be having the highest energy. That is the purple light will be having the highest energy. Gets absorbed by the first cell, which is transparent to all light of lower energy. That is the blues, greens, yellows and reds. The remaining things can pass through the material, but that transparent, the other, that is the blue light, green light, yellow light, red light can pass through it, but that light cannot be absorbed by that material. Only purple wavelength light can be absorbed by that material because of having the high band gap. Next one is the second cell absorbs the next highest energy, that is the blue light, followed by purple. The next highest energy is the blue light. So blue light is having the next high energy means, so the second layer will absorb, the purple layer is completely absorbed by the first layer. So the blue light is absorbed by the second layer, and the remaining greens, yellows and reds will be transparent to this layer. That is, the second layer will not absorb the green, yellow and red. It will absorb only blue. The purple is already over in the first layer. Second layer is blue. Third layer is yellow. Likewise, it will go. Right, and so on. You can see, one way to improve the only way to improve the efficiency is to split the spectrum. You can see, incoming full spectrum is passed through the first material. We have two materials. The first one is a high band gap cell, and the second one is a low band gap cell. That is, the top cell absorbs high energy photons. You can see it now. The top, when I focus on the complete solar radiation on the top cell, only some part of it is absorbed. The purple and blue light is absorbed by the top cell, and the remaining light is passed through the high band gap cell, and it is falling on the low band gap cell. That is the first energy. That is the blue and purple light having high energy and low penetration depth. Low lambda means low penetration. That is, they will be absorbed by the top layer itself, and they cannot be passed through the second layer. So what of the rest of that is the green, yellow, red, it will pass through the first band, will be transparent to these radiations are transparent to the high band gap material, and they will pass through the high band gap cell, and they will be falling on the low band gap cell. The top cell absorbs the high energy photons, the bottom cell absorbs the low energy photons. And there are two ways to manufacture these multi-junction devices. It is called generally it's nothing but a stacking. Stacking means stacking the individual single junction solar cells in descending order of band gap. Right, so there are two ways of manufacturing these stacks. The first one is a mechanical way, the second one is a monolithic way. The first one is a mechanical step. How we will make it? Say for example, let's take the example of a cadmium telluride. First I will fabricate a cadmium telluride solar cell, then I will fabricate a cadmium sulfate solar cell, then I will keep one on the other, then I will mechanically stack it. Right, then I will get a mechanical stack. So two individual solar cells are made independently. They are mechanically stacked one on top of another. The other one is a monolithic way of making the multi-junction solar cells. What is that? One complete solar cell is made first. So one complete solar cell is made first, on which by doping process we can make the second and third and fourth layers likewise. First bottom layer is fixed, and on which we will keep the top middle layer and the top layer. That's why you can wait. So we are discussing about one different solar cell. An example of this multi-junction solar cell called gallium arsenide multi-junction solar cell. It's a triple junction solar cell which uses 3 layers. The top layer which uses 3 layers, that is gallium arsenide, germanium and gallium indium phosphate layers. These 3 are the 3 different materials which are used for the manufacturing of this solar panel. One more thing, this is a solar panel which is used in the space applications to power the satellites. So the bottom layer is a germanium, the middle layer is a gallium arsenide and the top layer is a gallium indium diphosphate. That is, you can understand that the gallium indium diphosphate is having the highest band gap and the gallium arsenide having the lowest band gap, and germanium is having the least band gap. Germanium band gap is 0.7 electron volts. Gallium arsenide more than 0.7. Gallium indium diphosphate more than gallium arsenide. It is how it will be made. Right. So bottom contact and the top contact. That A by R is nothing but anti-reflective coating. It is how. So this type of thing is solar cell is produced by Spectrolabs. Spectrolab is one company. It is producing this kind of solar cells, and the efficiency is the reported efficiency of this type of solar cell is 40.7% with a solar cell structure operating at 250 suns. The efficiency is very high, 40.7. At what radiation? 250 suns. What is 1 sun? 1000 watt per meter square. How can we get 250 suns? 250 suns will be possible only in the space, that is the extraterrestrial radiation only. So that is, these solar cells are used to power the satellites in the space, where you will get a more amount of solar radiation. More than 250 suns of solar radiation is available in the space. Thank you. And with this we have ended our 5th unit.